Hi everyone, welcome back. So in the previous video we started looking at how we can set up two oppositely charged parallel plates, and our goal here is to now find the electric field strength between those two plates. Okay, so key knowledge focus for this video is we're going to look at these equations here, okay, and use these equations to develop this idea of this field strength between the plates. And then we can also, in the next video, do some questions applying these two equations along with this one here. You should be familiar with this one. This is just the electric force equation that we developed in the previous videos. Mainly we're just going to be looking at this equation here and how we can get this electric field strength equation from that. Okay. All right, so first we've got to talk about what voltage is. All right, now you've probably done voltage in year 11 if you did physics in year 11. The way that we're going to think about voltage in this context is that it represents work per unit charge. Okay, just like field represents force per unit charge, voltage represents work per unit charge. Okay, so what that means is, let's draw a little diagram here. So here's two parallel plates, and the voltage difference between the plates might be 1.2 volts. Okay, if this top plate is positive and this bottom plate is negative, what's going to happen when you sort of place an electron here, okay, just above the negative plate? Well, think about it. It is going to want to accelerate towards the positive plate. Okay, negative electron gets attracted to the positively charged plate up the top. Okay, so the field, the electric field between these two plates, is doing work on this electron to make it accelerate that way. Okay, how much work is done on this electron? Well, let's not call it an electron anymore. Let's just call it a charge of some kind. Well, it depends on what the charge is. Okay, if this charge is 1 coulomb, then the work done in joules is simply going to be the potential difference between these two plates, which is 1.2 volts multiplied by the size of the charge. So 1.2 volts times 1. By the end up here, it will have gained, because it's increasing its speed, it will have gained 1.2 joules of energy. Okay, if instead the charge was 2 coulombs, how much energy would it have once it reached the other side? Well, 1.2 volts, that's the potential difference it's moved between. The size of the charge is 2 coulombs, so it'd be 1.2 times 2 coulombs, 2.4 joules. Okay, so voltage represents how much work is done per unit charge on your object. Okay, and we can set that up for ourselves in an equation. We can write it like this. Okay, the work done is just the charge multiplied by the voltage, or if you prefer, you can rearrange it and write it in terms of voltage equals work done per charge, which is what the definition of voltage is, work done per unit charge. Okay, so hopefully that gives you a little bit of an idea of what voltage represents. We're going to be using it this way in the context of these parallel plate diagrams and talking about the energy transformations that have occurred. All right. Similarly, let's just redraw this diagram slightly differently. Okay, let's say I now have a positive charge just above the negative plate. Okay, and what we want to do is we want to make that positive charge move across this gap towards the positive plate. Okay, now your positive charge is going to resist that because it doesn't want to go near the positive plate. Okay, because they're both the same sign charge, it's going to get repelled. Okay, it wants to be down the bottom near the negative plate. So we ourselves have to do work on that charge to bring it up to here. Just like you would say if you wanted to move a box from the ground up to a higher shelf, you have to go against gravity, you have to work against gravity, you have to do work on that box to lift it up to that higher shelf. Same thing here, okay? Alternatively, what you could do is you could, again using a gravity analogy, give this charge some speed, okay? Give it some initial speed up this way. What's going to happen is it's going to get shot upwards, it's going to slow down because it's getting attracted back down towards the negative plate. And if it doesn't have enough speed, it won't reach the top plate. It'll just sort of slow down, stop, and then make its way back down to the negative plate, okay? So there's a certain amount of energy that you need to give that charge in order to make it reach the other side. How much energy do you need to give it? Well, that's this equation here, okay? So we'll see that pop up later on when we do some example questions. All right. So here's a question for you. Two parallel plates are set up to be 10 centimeters apart with a voltage of 20 volts. So if we draw a picture, it looks something like this. Say that's positive, that's negative, 20 volts between the two plates, and they are 10 centimeters apart, or 0.1 meters. Cool. An electron is placed at the negative plate, so down here, or just above the negative plate. What's going to happen is the electron is attracted to the positive plate, and so it accelerates across the gap. And that's what we were talking about in the previous slide. So it's going to accelerate this way, be attracted towards the top plate. Question, what is the gain in kinetic energy of the electron? And the hint is, work has been done on it. Okay, what is the gain in kinetic energy? Well, we know it's just speeding up. It's being accelerated towards the positive plate. So its kinetic energy is increasing. The electric field between the plates has done work on the electron to increase its kinetic energy. How much work has been done on it? Well, that's our little equation. Work equals Q times V. So the Q charge on the electron, 1.6 times 10 to the negative 19 coulombs, multiplied by the voltage or the potential difference between the plates, 20 volts, and we get an answer of 3.2 times 10 to the negative 18 joules. Okay, so not much work. It's a very small number, but you've got to remember electrons are tiny. Their masses are really, really small, so it would probably accelerate actually quite quickly. All right, now, second part of the question is, will there be any difference if the plates were spaced 50 centimeters apart? Well, in terms of the work done on the electron, no, there wouldn't be any difference. Why is the reason for that? Well, look at the equation for work. Nowhere in that equation does it ask us to use any values for the separation between the plates. Okay, it's simply just a function of the charge that we're talking about and the voltage or the potential difference between the plates or across the plates. Okay, it doesn't have any idea about what the distance between the plates are. Okay, what you would see though is you'd see the electron or the charge or whatever you've got, you would see it accelerating less quickly. Okay, so it's got a longer distance to cover. All right, it's almost, how can I put it with an analogy with gravity? It's almost like saying if you drop something from 5 meters above the ground on Earth versus if you were to drop something from 15 or 20 meters above the ground on the moon. Okay, I'm going to fudge the numbers a little bit here, but in both instances, the object will reach the ground with the same speed. Okay, because first of all, it doesn't have to travel as far on Earth to reach the ground, but Earth's gravitational pull is stronger, so it would accelerate more quickly. On the moon is much less massive than the Earth, so its gravitational pull would be less. But because you're dropping it from a greater height, it's got more time, it's got more distance to cover to make up that that extra speed that would have been lost if it was just dropped from 5 meters. That's kind of the same thing as what's going on here. Okay, by the end of this interaction between the electron and the plates, the electron will still have gained the same amount of energy. It's just that it took longer to do so when your plates are spaced more further apart. Okay, cool. So now we're ready to start looking at what is the actual value of the field between the plates. Okay, so first of all, to give you a reminder, the work done on an object by a constant force is equal to this here. Work equals force times the distance. Okay, this is going back to area of study 3 when we looked at energy. Okay, now we're just taking for granted the fact that the electric field is constant between the two parallel plates. All right, and the force, the electric force acting on a charge, is equal to QE. If E is constant, Q is just a constant as well, because it's just the magnitude of the charge. That means the force acting on the charge is also constant. Okay, so what's going on between your plates is, that's positive and that's negative, the electron in here is always having the same magnitude force being applied to it during its travels between the two plates, which means its acceleration will be constant. Okay, and so what we can say is, because there is constant force being applied to this charge, then this equation does apply. Okay, so the work done on this charge as it moves from here to here is equal to the force that's being exerted on this charge multiplied by this distance d. Okay, now from the previous couple of slides, we just worked out that the work done when a charge moves across a potential difference is equal to that. From the very previous slide, we worked out that that's also the work. Okay, so we've got these two expressions for work. So what we can do is just make them equal to each other. You get something like that. Okay, and we also know that the force that is exerted by an electric field on a charge is equal to this. And so if I replace this F here with QE, I end up with this equation. And what you can do, you divide both sides by Q, they cancel out. You end up with a nice little equation for yourself. V equals E times D. Or if you want, you can rearrange it and solve for E, and you get this nice expression, which is exactly the electric field between those two parallel plates. Okay, and the electric field is simply just equal to the voltage, or the potential difference across the plates, divided by D, which is their separation. Okay, so that's the potential difference across the plates, and that is, that is their separation. Okay, and you can see those two values are a set. Okay, so it doesn't matter where you are in between those plates, the separation is just whatever the separation is. The voltage or the potential difference is just whatever it is. There's no variation in anything. Okay, so no matter where you are in between those parallel plates, the electric field is going to be the same magnitude. Okay, and it just depends on the voltage and their separation. All right, now you may be wondering, well, what are the units of this electric field? Okay, well, if we're talking about a point charge, so if you're talking about, positive charge radiating its field out into space around it, okay, and you want to work out the field strength, say here, that would have units of newtons per coulomb. When we're talking about parallel plates though, because of the way that we calculate the field, okay, it's more appropriate to use units of volts per meter. Okay, so it's an alternative unit. They're equivalent to newtons per coulomb. Okay, it's the same thing. Both things are talking about the electric field. It's just that when we talk about parallel plates, you should probably use volts per meter when you write down your answers. For point charges, use newtons per coulomb. Okay, cool. So that's it for this video. Go back and make sure you understand the equations that are involved. Okay, mainly we are looking at this equation here, E equals V over D. Also make sure you understand this equation the work being a function of the charge and the potential difference. As long as you understand what those equations are talking about and how the energy of your charge changes as it moves between the plates. It could either be speeding up if it's getting attracted to the other side, or it could be slowing down if it's being repelled by the other side. As long as you understand all that, then we can start doing some questions in the next video. Okay, so I'll see you then. Take care.